The next speaker is Johnnie Hancock from Keysight Technologies. He will talk about characterizing the physical layer of KNFD. Johnnie graduated from the University of South Florida, and he was working since 1979 with Hewlett-Packard, which is now Keysight Technology. And he holds a patent for digital oscilloscope trigger application. He is currently responsible for the worldwide application supporting the Keysight's digitizing oscilloscope, and he gives regularly speeches on technical conferences. So welcome, Johnnie, and I hope you can take the screen and present your paper. Yeah, the screen is yours.
Okay, thank you. Let's get started here. So welcome to my presentation on characterizing the physical layer of KNFD. So the objective of this presentation is to talk about the practical sense of how to perform critical dynamic pulse parameter measurements, including transceiver loop delay and recessive bit width on KNFD using oscilloscopes. So the focus here is the practical, the how-to. Mr. Heel presented during the last iCC conference the theoretical on these same exact topics, transceiver loop delay and recessive bit width. The second half of my presentation is going to focus on I-diagram mask testing. So I-diagram testing provides a physical layer analog signal quality test all in one composite measurement. This is a measurement that perhaps many engineers haven't been using. It's very common in higher speed serial data analysis, such as USB 2.0, PCI Express. But as data rates of CAN-FD, as well as what we just heard about CAN-XL, go to higher and higher rates, it's more important to get an overall look at the bus of all bits overlaid on top of one another to get a feel about the signal quality of the bus. So let's take a look at our agenda. First of all, we're going to talk about some tips on probing the differential CAN or CAN-FD differential bus. Then we'll talk about what is transceiver loop delay, why is symmetry important, and then how to trigger on isolated bits, and we'll talk about why that's important. The measurements themselves, making loop delay measurements, recessive bit width, is fairly straightforward. Then we'll jump into I-diagram mask tests, and then I have a few technical resources to share with you. So here we see two different views of probing the differential bus. Now, first of all, let me emphasize that I believe it's very important to use the differential probe. Many engineers, simply because they don't want to spend the money for a differential active probe, they'll use two single-ended passive probes and then use the scope's waveform math to compute the difference. There are some drawbacks to that. Number one, a standard passive probe has relatively high capacitance. That's going to load your bus. Number two, you can't trigger on the differential signal if you're probing it single-ended. You can't trigger on a waveform math. Also, the update rate, responsiveness can be rather slow with using waveform math. So here are two different views using a differential probe. The one on the left is probing it dominant bit high. And this is the way I believe most engineers do it. You connect the plus input to CAN high, the minus input to CAN low. This is very intuitive. However, a high will be a logic 0 and a low will be a logic 1. The way I prefer to probe the differential bus is to hook it up what many people would say backwards. Connect the plus input to CAN low, the minus input to CAN high. Now, a high is a logic 1, a low is a logic 0. And also, if you probe this way, you will have the same polarity for transmit signal, receive signal, and the differential bus signal. And this is the way it's always shown in CAN timing diagrams. So throughout this presentation, I'm showing lots of waveforms. Just remember that I'm always showing the differential bus as dominant bit low, but you can do it either way. So let's talk about transceiver loop delay. This is a block diagram of a transceiver I received from Infineon. I consulted with Magnus on this. Transceiver loop delay is the delay time from the transmit input pin to the transceiver through the transmit half back through the receiver half to the receive pin. There can be a difference between the delay time from when you're going from a dominant bit low to dominant bit to a recessive bit versus a recessive bit to a dominant bit. The way it should be measured is always from the 70% to the 70% when it's going dominant to recessive, and from the 30% to the 30% when it's going recessive to dominant. And then, depending upon the symmetry of this, this can significantly affect your recessive bit width, which is always measured from your threshold levels. Now, again, I'm showing dominant bit low, so that's from -0.5 to -0.9. If you're probing at dominant bit high, the way I believe most engineers do, then you would measure from +0.5 to +0.9. Now, the reason it's this diagram, what I'm showing, it's important to make this measurement on an isolated recessive bit. And what we mean by isolated is that it's preceded by 5 dominant bits and followed by 1 or more dominant bits. And the reason for this is for what's called intersymbol interference, or as Magnus just illustrated, you can have ringing on the bus, and preceding bits can affect the timing of following bits. So let's take a look at a diagram that I think illustrates this. Here we show 2 different patterns. The pattern on the top, pattern A, is 4 dominant bits. Then we have 2 different signal cases. The black trace represents a signal that has some overshoot and ringing, perhaps some reflections. The red trace represents a very flat response. Now, if we look at the timing of the rising edge, so that would be dominant to recessive, the timing of those 2 signals is virtually the same. But now take a look at pattern B. The black trace that has the overshoot and ringing goes to a much higher absolute voltage, or in this case, a larger negative voltage. And when it switches to rise back up to a recessive level, it takes longer to get to the threshold level with a fixed slew rate. Therefore, you have a timing shift, so you have a timing error. And so if you always make the measurements with 5 preceding bits, you can negate out the effects of this timing. However, it's probably a good idea when you make these measurements, do it with 5 preceding dominant bits, and then also do the same test with perhaps just 1 dominant bit preceding the edge that you're making the measurements on. And then compare the difference. So how do you synchronize? If you're making these measurements with an oscilloscope, how do you actually synchronize on this bit pattern? This is really the heart of this part of the presentation. I see that you have 3 choices. Number 1, you could capture an entire CAN FD frame on the oscilloscope, single shot, then scroll through and in the data phase, look for that pattern and perform your measurements. The drawback of this method is that it's single shot and you can't get statistical information or dynamic information if there's any jitter or variations from measurement to measurement. Number 2, you could program in a complete null data set, all zeros. That will create a series of isolated stuffed bits. By definition, this measurement is performed on stuffed bits. Then simply trigger on the stuff bits using time qualified triggering, and then you could make repetitive measurements. And all of today's oscilloscopes have the ability to do pulse width triggering. Number three, and this is really the focus of this presentation, is to use time qualified pulse width triggering along with zone qualification triggering on a random data phase bit based on the repetitive acquisitions. Let's see how that's done. So here I show an example. We're probing the TX signal using a standard high impedance passive probe, and the scope is set up to trigger on 5 dominant bits. Now this particular waveform is based on an FD data rate of 8 megabits per second. So I've set up the scope to trigger on a low pulse or a recessive series of recessive bits between 575 nanoseconds and 700 nanoseconds. At 8 megabits per second, 1 nominal bit would be 125 nanoseconds, 5 nominal bits would be 625. So bracketing it between 575 and 700, you can lock in on those 5 preceding dominant bits. But that's only half the story. So as you can see up here, I have the scope scaled at 125 nanoseconds per division. Sometimes you get the single recessive bits, but sometimes you get multiple 2 bits, 3 bits, 4 bits, up to 5 bits. The next step is to use zone trigger. Now, not all oscilloscopes have zone trigger, and they go by different names in different manufacturers. Some scopes call it visual trigger, some call it InfiniScan trigger. It's a post-process trigger. Some are hardware-based, they're very efficient, very reliable. Some are software-based, very slow and less reliable. So if you position a zone where you expect that falling edge after 1 recessive bit, you can lock in and guarantee that you have that recessive bit isolated. The next step is to simply make the measurements. Now here I've rescaled the signal so that we can see separation of the transmit, receive, and the differential bus signal. If I was doing these measurements myself, I would actually have them all overlaid and have maximum deflection on these signals so that I get maximum resolution. But I've separated them here simply so we can see them clearly. So here we're showing the first loop delay measurement from recessive or from dominant to recessive, measuring from the 70% to 70% point, and we measure about 138 nanoseconds. Now, all oscilloscopes today have the ability to customize your threshold levels, either based on percent or based on a voltage level, regardless of the vendor. So remember, 138 nanoseconds. The next step, oh, by the way, just something quickly to show here. Notice that the RX signal arrives after the TX signal ends. So this shows you the reason why you have to have a secondary sample point for the transmitting node to sample its own bit in order to check for bit errors. But that's not what this presentation is about. So the next measurement is just the transmitter loop delay recessive to dominant bit. And there we measure 30% to 30%. Now we measure 122 nanoseconds. So remember, 138 versus 122, we have a difference of, I believe, about 16 nanoseconds. Next, we measure the bit width based on the threshold levels, this time from -0.5 to -0.9. And that's because I'm probing for dominant bit low. We measure 113 nanoseconds. The nominal bit width for 8 megabits per second would be 125 nanoseconds. So we shortened it by approximately 12 nanoseconds, which isn't bad. And that pretty closely correlates to the difference in our transceiver loop delay measurements. But this is not the only effect only cause for changing bit widths. There's more than just transceiver loop delay. A couple other effects are the actual dominant differential voltage level, as well as slew rate symmetry. So here we show a transmit signal going from a dominant to a recessive level. And on the differential bus, again, I'm showing it dominant bit low. In this first example, let's assume the bus level goes to minus 1.5 volts. When it's time to switch, there's a slight delay, and then there's a relatively fixed slew rate to get up to the threshold level. And so that defines the RX recessive bus width. So what happens if you go to a much lower dominant level, assuming dominant bit low probing? Now the signal has to transcend a much further distance up to the threshold level, and now you get, again, your recessive bit becomes shortened. Also, another effect will be the actual rise time and the fall time. The symmetry of rise and fall will affect it. So for our last measurement here on this segment, I'm just showing the recessive bit on the differential bus, and I'm making multiple parametric measurements, rise time and fall time. Here you can see we have a faster rise time than fall time by about 5 nanoseconds. And we're also measuring the recessive level, which on the scope is called V-top. It measures approximately 0 volts. And the base level, which is the dominant level, measures about minus 2.2 volts. So let's now talk about eye diagram mask testing. Eye diagrams provide a composite picture of the signal quality and signal integrity of your differential bus. It overlays all bits on top of one another relative to a recovered clock. And the recovered clock is based on where clocks are resynchronized, as well as based on the oscilloscope's much higher accuracy time base. And as I mentioned early on, this is a very common measurement on higher speed serial buses. Engineers really rely on this to give you an overall picture of the quality of your bus. So let's take a look at an example of how an eye diagram is created. Now here I'm showing a series of dominant and recessive bits. It would actually be based on many more bits than what we're showing here, but this will help illustrate it. The first step is the scope captures a series of pulses. Could be one frame, could be multiple frames. It then searches through and finds all the resynchronization points, which is the recessive to dominant bit transition, and identifies those resync points. Then it divides between those points bit times relative to the scope's time base. And it's much more accurate than a CAN bus, each node's clock accuracy. The scope's time base is typically has an accuracy just a few parts per million, or it could be a fractional parts per million. Once it has divided it up, then it steps down through the waveform, taking 2 bits at a time, and begins overlaying them to create the eye diagram. And there's your 1 bit time. And what it shows you is jitter, and variations in amplitude. You can apply a pass-fail mask to it, which the sample point typically is somewhere in the middle of the mask. And if the waveform violates the mask, that indicates a failing condition. So what does the eye diagram show? Well, on the vertical axis, it shows worst case differential noise or interference. It shows transmitter dominant level variations, which there can be some. It shows ringing, shows reflections, which we just talked about in the previous section. On the horizontal axis, it will show worst case jitter, worst case clock tolerance errors, bit time quantization errors, as well as slew rate symmetry or asymmetry. So let's look at some examples of eye diagram measurements I performed. This is on actually a 10 megabit per second system. This is a 2-node evaluation board I have. And this is a very clean eye that we have right here. And by the way, you can see the pass-fail mask is shifted slightly to the left. This is because I had a 60% sample point. So what I did with my system next is I forced it to have a clock tolerance error of -1%. Now, the worst case resynchronization of the CAN as well as CAN FD bus is 10 bit times. That's based on 2 consecutive stuff bits. Now, -1% clock tolerance or a +1% clock tolerance can result in up to 10 nanoseconds of timing error. And there we can see it very clearly. With -1%, the waveform starts creeping in on the right side toward the mask area. My next step was I set the clocks back to their nominal rates, and I added differential noise to the bus, but which might be something you might find in a harsh environment of a automobile. And there you can see the eye beginning to close vertically. This next example was something I accidentally bumped into. My 2-node system, the 2 nodes, the network length was very, very short, just a few centimeters apart. And what I decided to do is I ran over to the lab stock and I got 10 meters of twisted wire because I wanted to see how would this operate if it was in a vehicle with a long network. So I connected in my 10 meters of wire and it didn't work at all. And I didn't know why. And so I started snipping down my network length. I snipped it down to 5 meters. It still didn't work. I snipped it down to 2.5 meters. And this is what I saw when I looked at the eye. And now you can very clearly see the signals from the 2 different nodes. I'm probing at one end of this network. I have overshoot on one of the signals, and I have what's called a non-monotonic edge on the other. As soon as I saw this, I knew exactly what was wrong. We're seeing network reflections right here. When my bus was just a network was only a few centimeters long, my termination was at one end. I had a 60 ohm resistor in there, and it didn't matter because the network was so short. But when I extended it to 2.5 meters, now I'm getting all these reflections. And so what I ultimately did is I pulled out that one 60 ohm resistor, then I put 120 on each end, and that cleaned it right up. And now this last example is I added all of the errors, the 1% clock tolerance error, the differential noise from a nearby switching power supply, and this improper termination that caused all sorts of reflections. And now you can see the eye closing in. The red portions show where it's violating the pass-fail mask. And so there's my data valid window. I'm at high risk of this not working in the system with all these error components in there. Now, what is the mask based on? The eye diagram mask itself, the limits, the shape of it is very typical for a lot of serial buses. It's a 6-point polygon, but it is not defined by ISO. I personally define this mask because it didn't exist in any standards. I based the upper limits on the -5-point threshold, the lower limits on the -9-point threshold. And we have masks for both dominant bit low and dominant bit high. And the timing horizontal I based it on 30% and 80% because I factored in allowable clock tolerance as well as quantization errors. And this is what I felt was good limits. My recommendation is that ISO take a look at this and come up with defined standards so that all oscilloscope vendors can provide masks that are all based on the same standards. I'd just like to show you what a classical CAN eye diagram looks like. It appears there's a lot more timing jitter. It is not jitter. What it is it's the propagation delay, the 2 times to travel down the bus and back during the arbitration phase. And the sample point for classical CAN is typically shifted much further to the right. It also shows variations in various dominant bit levels being generated from different nodes. And it also shows you the arbitration phase bits and acknowledgement bits. So here we can see all of these together. So let's summarize what we've learned here today. CAN-FD timing parameters should be fully characterized with an oscilloscope using proper probing techniques. Hopefully with a differential probe, low capacitance, transceiver loop delay, symmetry, and differential bit width should be characterized based on isolated bit patterns. And I recommend you do it with, say, 5 preceding dominant bits as well as 1 preceding dominant bit. See what the difference is. Advanced oscilloscope triggering, including pulse width trigger along with zone qualification, can be used to isolate measurements on these specific bit patterns without programming something specifically in. And a high performance and pricey oscilloscope is not required for these measurements. A 4-channel scope with 200 megahertz bandwidth, 5 gigasamples per second is more than enough. You can get a scope with this level of performance somewhere in the 5,000 euro price range. You might want to add on software that could be 1,000 or 2,000 more if you want to decode the bus, trigger on bit patterns. And then also the differential probe, which is not cheap, will be a couple thousand. So you can get all this for under $10,000 from any vendor. And lastly, the eye diagram mass test provides a composite measure of signal quality. Now, a couple of papers I'd like to reference. Number 1 is a paper written by Magnus Maria Hill back at the 2015 iCC conference on the theoretical aspects of transceiver loop delay and bit width measurements. Also, Florian Hartwich presented a paper back when CAN-FD was first defined. I'd like to reference that paper. I've written a couple of papers, one on zone trigger, one on mass testing, and then the last one there you can see talks about intersymbol interference. So at this point, I'd like to turn it back over to the moderator. We don't have time for questions now, but I'll be back for the C3 coffee event if you have any questions. Thank you.